Imagine for a moment that you're looking out your window when a singular, bright light suddenly flares into existence in the sky above you. This dazzling star is as luminous as the full moon at night, perhaps brighter, and is even visible during the day. If you can see the light, you might already be in trouble, as that unexpected star is now flooding the atmosphere of the Earth with a catastrophic dose of gamma radiation and X-rays, stripping away our ozone layer and exposing us to the full fury of the sun's deadly radiation. And on its way, jettisoned out at 10,000 to 40,000 kilometers per second, a cataclysmic wave of stellar matter and debris hurtles towards our planet. The dying roar of an exploding star venting billions of tons of burning mass at us, ready to sweep across our planet's surface in a tidal wave of fire. This is a supernova. Or at least, it's one interpretation of what we might see if one were to occur near us. But how likely is it for this to actually happen? What constitutes near us on a cosmic scale? How close would a supernova blast have to be before life on Earth would be threatened? What might we on Earth actually experience? And what stars near us have the potential to detonate in this way? I'm Alex McColgan and you're watching Astrum. Join with me today as I discuss an event that could be an Armageddon in our lifetimes, or could be nothing more than a pretty twinkle in the sky. Let's start with the good news. Supernovae in our galaxy are not that common. While astronomers observe hundreds of supernovae every year outside our galaxy, this is mostly a reflection on how many galaxies there are in the universe. Closer to home though, within our own Milky Way, we likely only see about 2 to 3 every century. This means that the odds of one going off tomorrow are not that high. But they're not impossible. And according to archaeologists, the Earth has likely been hit by a supernova before in the course of its 4.5 billion years of existence. For starters, we exist in an area of space known as the local bubble, a relatively sparsely populated region of interstellar space about 1,000 light-years across that is thought to have been carved out by a supernova detonation 10 to 20 million years ago, which our planet would have been around for. I talk about that in another of my videos, which you can see here. Scientists have found evidence of another detonation that happened 2.5 million years ago due to a high concentration of iron-60 and manganese-53 in a particular layer of the geological record. This supernova happened far enough away to be harmless to us, but this might not always be the case. There are some scientists who believe that the extinction of woolly mammoths was caused by a massive piece of debris from a supernova crashing into the planet about 13,000 years ago. The impact site in question had magnetic spherules and radioactive potassium-40, a substance found in supernova ejecta. A smoking gun in the era most mammoths went extinct. Even before that, mammoth tusks from 34,000 years ago were found containing tiny impact craters from grains of slightly radioactive iron that had been traveling at 10,000 kilometers per second. If you can recall, that was one of the potential speeds supernovae explosions travel at. That can't have been a nice experience for the mammoths in question. An astute observer from this might be able to note an important fact, however. Evidently, if life began on Earth about 3.7 billion years ago, and we faced 3 supernova explosions that have impacted us in the last 20 million years, and life is still largely ticking along, my condolences, woolly mammoths, if you did die out from one of these, then supernovae as a whole can't be quite as destructive as my opening introduction made them out to be. And that's largely true, although it is, of course, a question of proximity. If I'm 1,000 kilometers away from a nuke going off, I have little to fear. But it's a different story if one detonates on my coffee table. And when it comes to supernovae, it turns out that the universe has relatively large coffee tables. To understand the scale of these explosions, it's necessary to understand the forces involved, which means we need to understand a little better about how supernovae happen. It turns out that there's two main paths stars can take to get to that explosive grand finale, although in each case it has to be the right kind of star. For the first path, resulting in a Type 1a supernova, it usually needs to be a white dwarf in a binary system that's gradually or speedily siphoning matter away from its neighbouring star until it reaches a point of critical mass. This path is not fully understood, but it's thought that a white dwarf, or a dense star comprising of mostly carbon in a giant superdiamond core, is normally finely balanced between two powerful opposing forces: electron degeneracy pressure and gravity. This simply means that atoms usually object to being squashed too much. Their electrons like to remain at certain distances from the nucleus of the atom, and will resist being pushed denser than this point. But gravity is an incredibly powerful force that seeks to draw matter closer, particularly in a dense mass like a white dwarf, where a section the size of a sugar cube has the mass of around a car. And in a binary system where the white dwarf is absorbing more and more matter from its neighbouring star, eventually gravity overwhelms electron degeneracy pressure and the whole house of cards collapses at once. Carbon fusion begins. Within a few seconds, most of the star undergoes fusion, forming into heavier elements and releasing a whole lot of energy as the matter in the star settles into its slightly more efficient new configuration. How much energy? Around 1/4 decillion joules. That's 1 followed by 45 zeros. If you claim you knew that number before, you're almost certainly a liar. All of this energy is released in just a few seconds. So naturally, the star ejects its entire contents out in all directions, sending it traveling at 6% the speed of light and unleashing a flood of mostly gamma radiation out across the galaxy. The brightness of this event is 5 billion times brighter than our Sun and burns for a few weeks until the ejector has traveled far enough that the overall energy level has started to dissipate. The second type of supernova, Type 2, is similar, except instead of involving a white dwarf, it involves a massive star at least 5 times more massive than the Sun at the end of its lifetime. These stars are still burning brightly, and rather than just electron degeneracy pressure, it's also the heat of fusion that keeps the star in balance. However, just like a Type 1a supernova, eventually balance collapses. This time is because the star runs out of fuel, and without this additional fusion energy pushing the star's mass outwards, electron degeneracy pressure on its own can't cope with the star's weight to similar effect. The only difference is that while some of a massive star will remain, often collapsing down into a neutron star or a black hole, white dwarfs usually vanish completely. Either way, the scale of material and energy released by a supernova is vast. So vast that unsurprisingly, anything immediately next to it is not going to last long. This is an energy powerful enough to rip apart a star. A planet is going to have no chance if it's in the immediate vicinity. Our own Sun, thankfully, will never go supernova as it's not massive enough, but if it did, there is a good chance the Earth would be either partially or completely vaporized, its rocky exterior reaching a boiling point thanks to temperatures 15 times hotter than the surface of our Sun, and being whisked away in the weeks of the supernova's passing. What is surprising, however, is how quickly this first wave of devastation would dissipate with distance. Indeed, vaporization is realistically not the largest threat a supernova poses. In 2011, experts from the University of Cambridge calculated that even planets orbiting their star at a distance of 15 billion kilometers, or about 100 times the distance between the Sun and the Earth, would remain intact and would instead simply be sent flying out into space now that there was nothing much left to orbit. Of course, such a planet's hypothetical ecosystem would probably have different problems to worry about. Things would get very cold very quickly. Of course, Even if the crust of a planet itself remained intact, that doesn't mean that life on said planet would be sustainable. Ignoring the light of a supernova outperforming the brightness of an entire galaxy sometimes, leading to blindness for anyone who saw it. Simply stripping away our atmosphere would carry problems. High levels of radiation, even if it didn't affect us directly, would alter the chemical composition of our atmosphere, negating our ozone layer, vastly increasing our odds of dying of radiation poisoning, and killing off phytoplankton in the ocean and causing mass extinctions as the consequences of that worked its way up the food chain. Scientists put this kill zone to be within 25 light years. Beyond that, the fury of a supernova begins to calm, as distance causes it to wear itself out. Although admittedly the asteroid that potentially killed the mammoths came from a supernova that was 250 light years away, if it happened at all, it was likely bad luck. Generally speaking, we wouldn't notice any damage from a supernova this far away. Its radiation levels wouldn't be high enough to cause mass extinctions. By 500 light years, we'd hardly notice the event at all, other than perhaps seeing a brighter star in the sky. Which leaves one important question. Within 300 light years, are there any supernova candidates we need to worry about? Thankfully, scientists are fairly confident that the answer is no. Massive stars are very noticeable, and the only two that are at risk of going supernova are Betelgeuse and Antares. Both of those are more than 400 light years away. White dwarfs are a little trickier thanks to their diminished brightness. They've been conventionally hard to spot, making it harder to predict whether we might be at risk from them. However, in 2013, ESA's Gaia Space Observatory released a massive packet of information in its efforts to map the stars that allowed scientists to identify 13,000 white dwarf stars within 326 light years of us. Thankfully, in spite of this large number, scientists remain confident that none of these are scheduled to explode anytime soon. Soon meaning within the next few 100,000 years. Speaking of Betelgeuse, there are some scientists who predict that this red giant might detonate much sooner than that, perhaps within the next few decades. Their research works under the assumption that Betelgeuse has a much larger radius than previously predicted, but if it's true, it might mean that we would get to see a local supernova within our lifetimes. Of course, according to some models, we would have nothing to worry about. The shockwave traveling out from Betelgeuse would take some time to get to us, and even once it arrived, it would be traveling with less force than the push of the solar wind. In other words, it wouldn't be our magnetosphere or atmosphere that kept us safe. The protective sheath of the sun's heliosphere would be enough to keep such a supernova at bay. So, there you have it. While supernovae are perhaps some of the largest explosions in the universe, through some fortunate stroke of luck, our patch of galaxy has nothing really to fear from them. The odds of us being hit by even the neighbouring stars like Betelgeuse that are scheduled to go supernova are incredibly small. True, Earth has plenty of cataclysms of its own, such as floods, earthquakes and hurricanes that can bring devastation to a community in a heartbeat, and space is still a dangerous place. But it's nice to know that of all the things we have to worry about, we can probably cross planetary annihilation from supernovae off our list. Supernovae aren't just some of the largest explosions in our universe. They're also a handy yardstick for sizing it. Thanks to Type 1a's consistent luminosity, there's some clever math scientists can do to calculate the distance between them and us. But why leave all the fun to the scientists? There's a free and easy way to join the fun thanks to the sponsor of today's video, Brilliant. I found that Brilliant's easy and interactive online courses have been a great way for me to get a handle on the maths that underpins the science discussed on my channel. But they don't just teach you maths there. Brilliant has thousands of lessons on science, computing and other STEM subjects, with more being added every month, including a chapter on supernovae as part of their course on astrophysics. If you want to expand your knowledge of the universe, or just brush up on some key skills, why not click my link brilliant.org/astrum in the description below to get started on your free 30-day trial. The first 200 of you will even get 20% off your annual subscription. Give it a try. Thanks for watching. If you want to learn more about threats from space, please let me know in the comments. Here's a great playlist you'll also probably find interesting. A big thanks to my patrons and members. If you want to have your name added to this list, check the links below. All the best, and see you next time.